All right, good morning, everyone. Welcome back. Hope you had a nice wellness day on Tuesday. Uh, so hopefully you got my note that I recorded a couple of short supplementary videos. One being the solution for assignment 2, the other being a little more about covariance and what how we evaluate it, because that's um, a thing that trips up a lot of people on assignment 2. In other words, what do the numbers mean, right? And how to evaluate what what covariance tells us. So we are currently in the midst of discussing more about random processes, and how we describe them, and how we can make use of things that, even though they're random and we can't predict exactly what they're going to be, if we know something about their properties, then that actually is going to be useful. Uh, okay, so does anybody have any questions at this point before we start off, either relating to assignment 2, which you probably got back yesterday, or any of the material? I'm going to do a quick recap of where we left off, but anything? Okay, then. So the last thing we discussed um, was the idea of autocovariance and autocorrelation. Okay, and these are basically ways that we describe random processes on the basis of kind of their average behavior, right? And so if you remember last week, we just looked at a couple of examples of random processes, and the fact that, again, each time you measure the signal, you get something different because it's random, okay? But they have things in common from the same process. And it has to do with, rate of change, or um, frequency content, as we're going to see a little more about that today. Uh, so they do have some common properties in spite of being random. And one of the ways to describe this is through the autocovariance or autocorrelation. Okay. And the idea in autocovariance and autocorrelation is to describe the statistical relationship between one time point in the signal and another time point in the signal, right? And so if the signal, like this one, doesn't change very quickly, then there's probably a range of time over which it has a relatively positive autocovariance, for example. And that's going to, kind of influence how fast it can change, because if, time point t+5 is highly related statistically to time point t, then, there's going to be limited in how much it can change. One way of looking at, say, autocovariance or autocorrelation is to say, if I measure my signal at time point t, how well can I predict what it's going to be at time point t+5 or t+10 or t+ whatever, okay? Because, how much information does knowing this time point tell me about some other time point? We like to think of it as in the future, but it doesn't have to be that way, right? If I know, if I measure my signal at time point t, you can say the same thing about, okay, what does that tell me about time point t-5 or t-10? How much are those statistically related, right? It kind of works both ways. But in these signals, we tend to think of them as kind of flowing forward in time, and that's fine. In an image, where we don't have a favored direction, really, you can talk about it going to the left or going to the right or going up and down, and it doesn't really matter. But the same principles apply. Okay. So you know, those are some of the kind of things that we mean, right, when we talk about this. And, you know, formally, and I'll step back one more step, right? We discussed the fact that if we have a stationary random process, then these quantities, autocovariance, autocorrelation, are really dependent only on one parameter, which we call the lag parameter, although, you know, it could be a lead parameter just as well. And just to be clear, right, this is in units of time, okay? So as I've written it here, this is a discrete random process. And so, you know, we can talk about K being an integer and this being in terms of time samples, time points of our signal. And really it just describes, you know, again, how far from the current time are we describing the relationship, the statistical relationship. The difference, of course, is autocovariance subtracts the mean, because we always subtract the mean from variance. That's my best way of remembering it. Autocorrelation doesn't subtract the mean. They are related, and I don't know if I brought this up, and we could prove this, but I'm not going to take class time to do this. Maybe I'll do it as a supplement. But, you know, you might recall that we did a little thing with the variance, and it turns out to be kind of similar. And hopefully you believe me when I tell you that the relationship between these two things is such that, let's write it this way, covariance is equal to autocorrelation minus the mean. Okay, so remember, since it's stationary, there is only one mean, right? Every time point has the same mean, and so we can just write that as a mu, right? That's the mean. When I write mu, I mean mean. So this is a thing worth remembering. Okay. Okay, so we can relate those two. So if you know one, you know, if I ask you to calculate something, one of these quantities, if it's easier to calculate one and then find the mean, do that, right? Generally, when I give you a problem, I'm thinking of the easiest way to do it, or the easiest way I can think of to do it. You can get there other ways, of course, but and if you get the right answer, that's fine in most cases. But sometimes some answers are just better than others. Okay. All right, so we'll kind of keep that in our back pocket, and also keep in your back pocket the idea that these express, you know, if how much information do I have about a future time if I know the signal at the current time. Okay, that's a way of thinking about it. There's a lot of different ways of kind of thinking about these things. We looked at those, and we looked at their autocovariance functions, which are also their autocorrelation functions, because these are all zero mean, right? If zero mean, then these are the same. And part of the point of looking at that was to demonstrate that the kind of features that we see, you know, in these random signals look a lot like the features that you see in the autocovariance function. Right? So if the autocovariance is wider and expresses an idea that we have kind of a positive autocovariance over a certain range of time, then our random process is going to kind of demonstrate that in how fast it changes and things, and generally, randomly, though, generate the same kinds of shapes of the same sizes, right? And so this was, again, on a different time scale for process 3. Okay, so those are some of the things that autocovariance describes. Process 4, the interesting thing about process 4 was that it actually had some negative components of autocovariance. And remember, a negative autocovariance is going to indicate that we're going to be tending to want to push to the other side of the mean instead of being on the same side of the mean. So by having negative autocovariance in a relatively short amount of time, that's actually going to push our random process to want to change quickly, right? If I'm above the mean within a couple of samples, it's really going to want to be on the other side of the mean, which means it's going to tend to want to change faster. Okay. So that's one of the things that a negative autocovariance means for us. Okay. So that left us with those things. We talked a little bit about, computing this, and this is more or less what MATLAB does when you call up its function. And better to look at it graphically, right? To find one time point of the autocorrelation, we take the signal, and this is an estimate, right? So we take the signal, we shift it by however many time points, whatever the lag parameter is. In this case, it's 1. Okay, we're going to take products of all of those things, and then we're going to average all of those elements this way to get an estimate of one component. That is, this is the lag 1 computation for the autocorrelation function. And it's going to repeat that for lag 2, 3, 4, and so forth, doing the same thing, but all you have to do is, shift one version of the signal by the appropriate amount. Okay. And, if you thought about it, you could probably come up with a way to write a program to do that. I'm not going to ask you to do that because MATLAB's already done it. But it's very, very procedural, right? You basically run 2 loops and advance this thing each time, and you could do that. Okay, and this basically states the same thing in text. Autocovariance would be done similarly. The only difference is that you would probably just subtract off the mean from the signal to begin with before you did all of this. And that would give you the autocovariance. Or you could just compute the autocorrelation and subtract off mean squared, right? So that would be done in a similar way. Okay. So there's one more way I want to look at the autocorrelation, and that is going to be kind of symbolically using our expected value operator, just to give you kind of an idea of how we would approach this. So let me draw on here. Okay. Actually, let's look at this first. Okay, so we have a random process, which is the sum of 2 signals, at least one of which would be random. And in fact, in this case, both are random. So F is the sum of X and N. X is stationary. That's going to be important. N is stationary. Both are random. Okay. And what do we know about them? Well, X has a mean of mu, whereas N has 0 mean. And then we're not being specific about their autocovariances, but they have autocovariance functions. Okay, we're not saying what they are. And basically, we want to find autocorrelation, autocovariance in terms of the things we have above, which are going to be mu, CXX, CNN. Okay. All right, so we're going to do things similar to what we did with expected values before. So first of all, it is actually going to be a little easier if we just deal with RFF first. So let's do that first. Tau is the lag parameter in this case, right? So that has units of time. And so by definition, this is expected value of f of t plus tau, right? That's how we define RFF. Now we can substitute in what f actually is, which is x of t plus n of t. Another bracket here. And then for f of t plus tau, it's basically similar, but with the time delay, tau, like that. Okay, and so again, that just comes from what we said f was. Okay, this is a linear operator. So what we're going to be able to do is multiply these out, and it'll be a sum of 4 terms. And of course, the expected value of a sum is the sum of expected values. And so we're going to basically break them into the 4 terms. I'm going to write them this way. So we get expected value of x of t plus tau, oops, plus, we're going to have a cross term. And another cross term. Okay, so those are the 4 terms I get. Now let's look at each of those. Well, by definition, this is Rxx. And by definition, this is Rnn, and we decided we didn't really know a whole lot more about that, except for the fact, if I scroll back a moment, so for Rxx, it has a mean of mu. Okay, so we can put that in terms of C if we just add his mean, which was mu. Okay. For Rnn, his mean was 0. So basically that means that this is equal to C sub nn tau. Okay, and that's as much as we can do with those terms because we haven't specified any more about those things. Now let's look at the cross terms. There's one more important piece of information here, and that was this. N of t and x of t are uncorrelated, which is another way of saying they are independent random variables. Okay. So that is going to allow us to do something to simplify here. And that is going to be, if they are independent, we can say this is true. But only because, I'll say, of independence. Okay. We can only do that move if the two things within the expected value are statistically independent of each other. Okay. Same is true here. Okay, so because they are independent, we can say this. Well, now we're just left with the mean values of each of those things. Mean value of X was, I'm going to use a different color now. So the mean value of X was mu, but the mean value of this was 0. So that cross term turns out to be 0. Same thing here. That's 0. That's mu. So it's 0. And ultimately, what we get for our final result, back to red, is going to be RFF is equal to CXX of tau plus mu squared plus CNN of tau. And that's as simple as we can make it. Okay. Any questions on any of that? And this is kind of an expected result. Basically, if you have the sum of two random processes that are independent of each other, then the autocorrelation of the sum is going to turn out to be the sum of their autocorrelations, which would be RXX plus RNN, but we wrote them in terms of C. Okay. And then just as another note, again, so if we wanted to do CFF, we could do all of that same stuff by including, X minus mu in everything. We have lots more terms to write down and cancel out, and it's just going to turn out to be a whole lot easier, I hope you can see, if we rely on this fact. And I'm going to write it this way, because we don't have a symbol for that. Right? That's the basic relationship. We used that further up. What is expected value of f of t? Well, I like using different colors here. Well, expected value of f of t is equal to expected value of x plus n, which is equal to, because this is a sum, I can break it into the sum. This is not the same thing that we did up here, because this was a product. Okay, I can always break out the sum. And of course, that's going to be equal to mu plus 0, which is mu. Okay, so back to red. This is simply going to be the quantity we just found. Minus mu squared. And so again, the autocovariance of the sum is the sum of the autocovariances, if they're independent of each other, uncorrelated with each other. Okay. Okay. So that's, hopefully you can see that's, a relatively simple way of kind of demonstrating some of these kinds of relationships, right? And a common mistake, so I'll point it out, is, well, two places where people make mistakes. So one is here, right? If they're independent, sometimes people will just say, oh, that goes to 0, but there were actually 2 steps here, and that depended on 2 things. One was independence, one was the fact that one of them was a mean of 0. If n was not a mean of 0, this term would not be 0. Okay, it's the product of those 2 means. So keep that in mind. Another thing that people do would be to break this into the product of expected value of n and expected value of n of t plus tau. But n is not independent of itself, right? Just as x would not be independent of itself. And so you can't break that apart because a random process can never be independent of itself. It's only when we have these cross terms, okay? Just one other thing, kind of foreshadowing, because we're going to talk about this in a second. These 2 terms are what we would call RFG and would be called the cross correlations. Between f and g. That's why we write 2 f's and 2 n's when we write these things, because that's the cross correlation with itself, therefore the autocorrelation. But we can also talk about correlations between different signals. I'm sorry, not FG. That's not good. That's what I want. RFN is the way we would write that one. So the cross correlation between F and N. Okay. Of course, this will be in the annotated notes.
Wait, is it F and N or is it X and N?
Oh, look what I did. Yeah, you're right. Boy, I gotta erase another one. Thank you. Thank goodness for the eraser. That's better. Yeah, okay. All right, so any questions here? You'll probably want to refer to this again. There is a similar problem on the homework. It's a little more, the one on the homework's a little more complicated though, sorry. Okay. So we'll keep that, and that's the end of that set of slides. All right, and so now we're going to move to the slides that are associated with today. And so today, the main thing we're going to do is talk about the frequency domain elements of this and how all this relates to Fourier transform stuff. And so we will get there. And just to mention, our friend, the cross correlation and cross covariance would be defined like this. Okay, and so basically it's the same idea. It's just that now you have 2 different random signals. And the idea here is, you know, as we kind of looked at it before, is that this expresses, let's say, if you know, let's say f at time t0, I'm going to say that way. How much do you know about g at time 0, t0 plus k? Okay, Okay, that's basically what, a way of looking at what this expresses. And so this really expresses a statistical relationship between two different random signals. Why is that useful? Well, I'm going to give you an example. So you might remember from homework, we had the EMG and EMG-FX signals, and I asked you to, basically we did the covariance of those two. So we did covariance EMG, EMG-FX, and when we looked at those, basically was kind of intended to, we see that the covariance term between those is much smaller, almost, like 1+ orders of magnitude below the variances. And the conclusion, again, if you look at the supplement, is that because this, even though it's a large number, absolutely, right, it's 3E5, that absolute value of that doesn't matter. What matters is what it is relative to these guys. And since it's a lot smaller than the variances, we might conclude that they're kind of, that they're independent with each other, that they're uncorrelated with each other. We say it, people say it both ways, so I kind of use both. And that seemed odd, right? Because EMG-FX is a filtered version of EMG. So they should be related to each other. Well, here's the trick, right? We were looking at these at the same time only at a lag of 0. Okay. And so instead, if we do this, the cross covariant, so this was covariance and does a temporal covariance estimate. XCOV does the cross covariance. It also does the auto covariance if you give it just one signal. Okay. But if you give it two signals, then it'll do the cross covariance between the two signals. Unbiased is a choice in this. If you look at the help file, it's got a couple of choices there. This is the one I prefer. This is the one that's consistent with my definition, but actually it's not the default way. So be forewarned, and in general, just be forewarned. Not always a great idea to use the MATLAB function in its default state. It's good to look at the help file and see what its default state is, because sometimes it might give you something that is hard to interpret unless you understand what it's really doing. Okay, so if we do this, and then I plot that, and then I change my plot a little bit here and there, so now we can see it. Okay, this is the thing I want to show you. So okay, we'll make it big. So what we were looking at when we did the COV function, we looked at this point on the cross covariance curve, basically lag 0, right? We were looking at them at the same time. And there's that 3E5 number, which we said was pretty small relative to the variances. But that's not the whole picture of the relationship between those two signals, because we have to look at them over the range of lags, because what the filter does, and actually we'll see most filters do, is it introduces a time delay. So if you look at them at the exact same time, you're not going to see the relationship. You need a bigger picture, and so you need to look at them at different time lags or time delays. And if you do that using the cross covariance, you find that over here, it's a lot bigger. It's, an order of magnitude plus larger, which is significant compared to the individual variances. And so as a result, there actually is a relationship between those two things that wasn't revealed by the COV function. Okay.
Dr.
Yeah.
Lelouch,
Yeah.
so when do you start getting significant, or when do you consider like a significant magnitude? Because like one of the covariances was like e to the 7, so, or like 3 e to the 7. So what would be like the range there? Like just try to get like a feel for it. Like what is significant?
Yeah. Well, and some of that is context. So statisticians will say that a a an R an R squared coefficient or an R coefficient, I guess, of around sometimes 0.4 or greater could be statistically significant, but even 0.2 might be something that people would pay attention to. Okay, so and it's fuzzy. So I hesitate to give an exact number, but if it's below 10%, right? If then that's probably not very significant. Around 10% still could be, okay? And so you ask a difficult question because there's no right answer to that. If you're, certainly two orders of magnitude lower, then yeah, probably not. 1 order of magnitude lower, yeah, but it's a question of context because here we know they should be related, right? And so if I look at what we get from this one, if I was just to take that, so this is what 6E6, and if I computed that using the R squared, I get about 0.4. That's enough to, that you can't consider them to be completely independent of each other, right? And it also depends on the question you're asking. So in this case, yeah, and they should be correlated. We know they should be because they come from the same original source. So 10% pretty iffy, and you could probably get away with assuming that they're independent. So yeah, if you need a number, I'll say that.
Okay. I mean, yeah, I think a little bit of like talking about like what ranges helps. So.
Yeah, and I mean, you understand. I mean, and this is kind of the thing we start getting into now, as opposed to the way you've kind of learned engineering before, which was there's a problem and there's an answer. No, engineering's not like that at all. There's a lot of gray areas and fuzzy things, and there are maybe lots of good answers, and maybe some answers are better than others, and there's lots of bad answers. But there might not be one right, perfect answer. Okay, so yes, and in things like that, where I'm kind of asking you to use your judgment, it's always a good idea to kind of justify it, right? Say, well, this is below 10%, and so we think that's pretty low, and so it's safe to assume that that they might act independently of each other. Or this is about 0.4, which is could be significant, and so we would probably not be safe to assume that they are independent of each other. When you say in those terms, that's a good way to produce answers to a lot of my questions, because it shows me you know what you're talking about, which is more what I'm concerned with. Okay, so keep that in mind. Okay, any other questions on that? So hopefully that example illustrates what's limited about just taking the covariance, and the fact that, and also tells you a little bit more about the cross covariance, right? Because again, if I know my input signal at time 0, that's going to be very predictive of what my output signal will be about 65 samples later, because 65 is the delay that that particular filter introduces into the signal. Right. Okay. And you might think, and it's true, that embedded kind of in the shape of this thing is something about the filter's impulse response, turns out. But that's not a thing we're going to get into. Okay. So yeah, I do want to introduce that idea of cross correlation. These are concepts that are used a lot in image analysis, signal analysis, data science, and things like that. We're going to use them a little and refer to them a little, but not as much as, let's say, we could. But it's good to have at least an idea of what those things are. Okay. Now the Fourier space. So we're going to start thinking about how all this translates into the Fourier space. So the power spectrum, it's something we've actually used a little bit, but haven't really named it. So we're going to name this. So if we have any signal, okay, we can define its power spectrum as its Fourier transform magnitude squared. Sometimes people will divide by time, just to kind of get units straight. We almost never actually do that. Okay, certainly in this class, because that's just a scalar. Okay, and so just making sure you're comparing apples and oranges. If you compare two of them, just do the same thing. So most of the time we will just consider the power spectrum to be just magnitude squared of the Fourier transform of the signal. So you measure a signal, you can take its power spectrum by Fourier transform magnitude squared. That's it. Okay. And of course we know multiplying by the complex conjugate gives us that. Or, you know, in MATLAB, use the ABS function and square the whole thing, term by term. Okay. Now, you know, the idea here is that as when we were just looking at magnitude, right? It just tells us the distribution of signal power throughout different frequencies, and that we've used it that way already. It is always positive and real, right? Because this has to be positive and real, so that's useful. It removes the phase information, which is, you know, again, mostly okay, but it's not a complete representation of how of the signal. Without the phase information, we can't invert the Fourier transform and get back the original signal. But tells us most of the information we usually want to know. How, you know, what is the frequency content? What frequencies have the most stuff in this signal? And discrete, same way. Again, we don't really we don't usually divide by 1 over n, but you do have to be consistent with however you do it. Okay. So we can take a 1-second recording of the EMG. We can find its, you know, again, Fourier transform magnitude squared. That's this power spectrum on linear scale. Sometimes we look at semi-log scale because you can't see what's going on here. Okay, and of course, again, this is only good up to the halfway point, which is probably around 500 or a little like 512 hertz there. That doesn't seem right. I think my frequency scale is wrong, so I should take some points off for that. In any case, that's the idea. So we've been looking at things like that all along. And if we were going to, you know, estimate, as I asked you to do in the homework, and again, almost any answer was correct. Most of the signal power would be between, say, 10 hertz and 100 hertz, where it kind of drops off. again, on the log scale, because, you know, down here, we're kind of an order of magnitude down from everything we have here. Again, that's fuzzy judgment call. But as in the homework, you know, it's important to look at these things in context, and it's also important to sometimes zoom in on parts of the plot so that you could see this. You know, you can kind of see that it goes up and comes back down here, but seeing the detail of what frequency ranges that is, it's worth exploring a bit. Okay. So we can make a judgment on this. Most of the signal power is in this range or so. A different one, this is a respiratory airflow signal. It's periodic, and of course what we expect from periodic signals is that they will have discrete frequency content. Remember, there was a supplement on that, the fundamental frequency and then harmonics of that. There's one there, there's one there. This is worth, you know, if you want to see these, use a semi-log. Okay. Well, random processes are going to have power spectra also. So, you know, again, we can take the individual signals here from process one and plot its power spectrum. The three elements are in different colors here. Of course, since this is random, this is random. Okay. When we start to look at process two, we see, okay, they do share something in common. Even though the spikes are very different and random through here, we see that the frequency content drops off in the same place for all of them. So that's something. Same with process three. This part, very random, very unpredictable, but the ranges of frequencies that are contained in there are similar, and they drop off in the same place. Process four, well, process four is weird, so we'll look at that one a little more later. It looks a little bit like that one, but it's not. But they do share similarities. You see it dropping off a little bit here. Okay, so this is the thing, right? The power spectra show that the frequency content is limited to low frequencies, in this case below 100 cycles per recording period, in this case below about 20 cycles per recording period. And the power spectrum is itself a random signal, right? Every time I do one of these and take a power spectrum of it, that's a random signal also. It's just random. It's a signal with respect to frequency. So we could take, if we wanted to know, say, the average properties of that random process in the Fourier domain, we could take a whole bunch of examples of these, take their power spectra and average them together, right? And I'll use this one as an example. And you would probably expect that, you know, on average, after I average all these things out and average a bunch of them out, this would show some content here and then start to drop off here and show very little content here as an average power spectrum for that random process. And in fact, it would. So we can talk about the expected value of the power spectrum of a random process by computing that kind of ensemble average of power spectra. And turns out there's a key relationship, which we could prove, we're not going to. You may take my word for it or look up the proof somewhere. The relationship between the power spectrum and the autocorrelation of a stationary random process. It has to be stationary, okay? Remember, stationary means statistics, random properties are shift invariant, and shift invariant remember, was kind of key to using the Fourier transform. Okay, so all this fits together. If we take the autocorrelation of random process and we take its Fourier transform, because remember the lag parameter is a time quantity. So we take the Fourier transform with respect to that time quantity, we will get the average power spectrum. Okay. Now, and this is a place where people slip up from time to time. This is the average power spectrum of the random process. It's not what you would get by measuring this and then taking its power spectrum, because you can see that's random. Okay, any one instance is random. So we're just talking about the average overall behavior. Okay. And so this does tell us about the frequency content of the random process on average. Okay, let's take a 2-minute break at this point. It's a good spot. And then we'll come back in a moment. Let's reset. There. Okay. All right, and we're back. Okay, so we have this kind of key relationship here. And again, that's a thing you should remember. It's not hard to remember. Okay? It might be, again, it might be a little hard to remember whether this is autocorrelation or autocovariance, but try to remember that. It's autocorrelation. Again, that's not going to make a great deal of difference, because the only difference between those is in the mean, which is going to mean it's only going to make a difference in zero frequency here, but we won't. It is technically the autocorrelation. Okay, so if we look at the spectra of random processes, and we have process 2, we had the 3 examples. So this is the same plot we saw earlier, okay, in 3 different colors. We take the FFT of the autocorrelation function, it would be this. In other words, this would be the average power spectrum of these guys. And so hopefully that's believable, right? That if I had a bunch of these, it would average out into something that looks like this. It is a Gaussian, by the way, because I made it. And so you can see that the autocorrelation, rolls off and goes close to zero at around 100 cycles, which is exactly how all of these guys behave. But again, individual examples are going to have more or less content at different frequencies within the range of frequency content of this thing because of the randomness. Process 3 behaves similarly. Its autocorrelation is a Gaussian, but a narrower Gaussian. Okay. And so they all roll off, the same place that the average power spectrum rolls off, which is what we expect. Process 4, remember this guy who's kind of weird, had the negative autocovariance elements? Well, this one behaves a little differently in that it actually has an emphasis on higher frequencies and then rolls off. Okay, and so as a result, it's a little harder to see, but hopefully it's believable because these spikes get a little more, you can see a little increase just like on average there, and then these spikes get a little more prominent throughout this range of frequencies that are emphasized in that guy, and they all kind of roll off at the end there, which you do see here. Okay, and so this is a case where, again, we're emphasizing high frequencies, which is going to contribute to faster changing of the power spectrum. And we interpreted in the time domain, when we looked at these negative things, we interpreted, if there's a negative covariance relationship there, it's going to want to tend to push to the other side of the mean, which means it's going to want to change faster. Well, we can look at the same, we can interpret the same idea in the frequency domain with its power spectrum and say, oh, that random process has an emphasized level of certain high frequencies, so it's going to want to change fast. And so, these are all different ways of looking at the same thing. So you can look at these, part of the point of this is you can look at these in the time domain by way of the autocorrelation function and make interpretations there. You can also look at them in the frequency domain and make interpretations that way, and they're just different ways of looking at the same kind of properties. Okay. Okay, and so, basically this says in words what the point I was just demonstrating, right? The power spectrum gives the average frequency content that you'll find in random samples of that random process. And of course, that relates to features that you see, right? If you're restricted into having higher frequency content, your random process can't change as fast because it doesn't have the higher frequencies required to do that. Okay. Now, there's a limiting case, right? If a random process has an autocorrelation of a delta function, then let's talk a little bit about the features in the random signal. And it turns out that the true autocorrelation of process 1, you'll notice I skipped process 1 up till now, is that its autocorrelation should be a delta function. So remember, when we calculate autocovariance, we get an estimate. So that approximates a delta function, but it's not a perfect delta function because it's just an estimate. Okay. But what does that say about in the time domain? Well, let's say we had, oops. So let's say Rxx of tau was a delta function, right? So it would be something like that. What are we saying? Well, we're saying that the correlation between a time point and any other time point is 0, or the covariance is 0. And remember, 0 covariance implied statistical independence. So what we're saying here is that any two time points in this signal are statistically independent of each other. There's no influence. There's no ability to predict from one time point to the next because they aren't tied together at all. Well, what is the power spectrum? It's the Fourier transform of that, right? And the Fourier transform of a delta function, sometimes I didn't write it this way. I know I wrote it as P, but sometimes we write it as SXX for spectrum. Well, the Fourier transform of that delta function is a constant. And by the way, this delta function is weighted by the variance, and so the height of this will be the variance. What does that say? Well, it contains all frequencies, right, in equal amounts. And so as a result, this is what is called white noise. White being the idea that if you combine all, colors of the visible light spectrum, you get white, which is a bit misleading because, that might be physically true, but the way we perceive light in 3 dimensions is a lot more limited, right? We only need 3 colors, really, red, green, and blue, in order to perceive white. But so much for that. Anyway, white is meant to imply equal amounts of the whole spectral space. And so this is how white noise is defined. Okay. It is uncorrelated with itself, except for at time 0, where it can't be uncorrelated at the same time. So that represents the variance, right? And so, well, let's define it specifically. Okay, when we say white noise, we mean 0 mean. That's not explicitly stated, but it should be. Its autocorrelation, which is also equal to its autocovariance, is equal to its variance, delta function, its power spectrum, is equal to a constant value of its variance. That's what we mean. So white noise is a shorthand way of saying that. Okay, so if I say, oh, this thing is a white noise process, you can immediately, with variance 10, you can immediately go to those properties of the white noise process. Okay, so process 1 was actually white noise. And of course, when we look at these, now that we know that, right, hopefully you can say, well, okay, it's believable that it might have equal content at all frequencies. If I take 1,000 examples of this and average them together, that's what I get. Okay, so basically I did that ensemble experiment where I take 1,000 of these samples from the random process, take the power spectrum of each one, and then average all of those together. This is what we get. Okay. And so it should, after averaging more and more of them, it should converge to a constant across the power spectrum, which is what we expect. There is actually a script on the website. Let me go here. There it is. And so, you know, you could refer to that, play with it if you want to. Obviously, if I generate more examples of the white noise, then it should converge to a smoother and smoother estimate, and look more and more like a constant value. And so that's using 10,000 of them. So, you know, do you believe that that's got equal content in all frequencies on average? Hopefully you do. Okay. Okay. So that's a way, you know, you might try to prove that. If you had some noise that you were measuring, you might take a bunch of measurements of it and do this kind of averaging to just see if you can justify calling it white noise or not. Okay. Now a little more terminology here. So you'll see references to Gaussian white noise. And the thing I want to point out is that this is a special case of white noise. So one of the things we didn't specify here was we didn't specify anything about its temporal statistics. Remember, well, we said what its mean would be, and we said what its variance was, but we didn't say what its probability density function would be or what its histogram would look like, because it could be anything, in fact, and still have these properties. So the idea that you'll see referred to sometimes as Gaussian white noise means that its PDF obeys a Gaussian or normal probability distribution with some mean and variance. Okay, white noise means that the samples are uncorrelated, but white noise could doesn't have to have a normal distribution. Okay, in fact, well, I think I have a script that demonstrates that too. That's not it. Sorry. Is it this one? Yes. Okay. So I'm going to generate two different kinds of white noise, one being Gaussian white noise, one being uniformly distributed white noise. And I didn't test this, so hope it works. Okay. That is not a thing I wanted to do. Sorry. Hopefully you saw this before I messed with it. That's how we do it. Okay. Okay, so basically I've generated two different kinds of noise here. One is Gaussian distributed, one is uniformly distributed within the 1-0 range. You can see they don't look that different, except maybe the range of values. If I look at their histograms, you can see their histograms are very different. Okay. The Gaussian, again, and they should be, right? The Gaussian looks something like a Gaussian curve, whereas the uniform should converge to just a rectangular function there. So they can have different histograms, therefore different probability density functions, but their autocovariances are in fact the same. They look like delta functions, right? Remember, this is estimating the autocovariance. And their power spectra also look the same, At least they did before I messed with one of them. And they look like they have all frequencies at a constant level. Again, if we take a lot more examples, they will converge to a constant. Okay. So the point there is that not all white noise is Gaussian. Okay. We can have other distributions as well, but if I say, okay, I have a Gaussian white noise process with zero mean and some variance, you know everything you need to know about that, right? You know it's white noise, and therefore you know it has these properties, and you know its probability density function. Okay, which is, you know, not necessarily specified by the fact that it's white noise. You know that it's fully specified by having a mean and a variance, because that a Gaussian or normal distribution is fully specified by knowing the mean and variance. That's all you need to know. Okay, and so if you have those facts, you could sketch an expected histogram that would be a Gaussian function with a, you know, sigma determined by that. And so you know all about the temporal statistics that you would get from this. And you also know the noise power spectrum, which would be a constant, right? And you know what the autocorrelation function is. It would be a delta function. Okay. Any questions about that? Well, a lot of times we talk about white noise, and a lot of noise is well modeled as white noise. So it's a very useful concept, and that's the language we, you know, in the field, that's the language people use. Is it white noise? Okay, that's enough to communicate a lot of information. Now, there are other kinds of noise. I think there's pink. I think there's a lot of, you know, varieties of colorful noise that have certain specific properties, but you will not hear about them as much as you hear about white noise. Questions? Okay. Well, I'll leave the thought problem since we're almost out of time. If you want to think about the other extreme, it's a good way of kind of testing your understanding, right? Because so here we said, okay, white noise, where's my white noise? White noise has an autocorrelation of a delta function, and therefore its power spectrum is a constant. What if we had a random process where the autocorrelation was a constant function? What would its power spectrum be? What would examples of that random process look like? I'm going to throw that out there and leave it. Maybe we'll discuss it at the beginning next time. But things to remember, okay? So this is kind of summarizing. Autocorrelation or autocovariance describe the statistical relationship between samples a given time or an imaging distance apart, right? And they definitely influence the features in the random signal. So that describes the time domain. The Fourier transform of the autocorrelation describes how these things behave in the frequency domain and tells us the average, remember average, power spectrum of the random process. Therefore, it tells us about the frequency content in the random process. Okay. That's where we're going to leave it today. Next time we will apply this to a simple system and see, you know, a little bit of a practical application of some of this, and justify some of the things that we actually do in signal processing. And next time will be the last material that will be on our first exam, which is coming up in like 2 weeks, something like that. Okay. Last chance for questions.
So in MATLAB, for computing the autocorrelation, do we
Mhm.
also just use the X covariance function for that and then just add the mean?
Yes. Well, no, well, yes. Well, actually, I think there is actually an X core function also. Am I right about this? Yes. So there is a similar function that actually does the correlation, cross correlation.
Okay, cool, thanks.
Yeah. So yeah, I should have pointed that one out. But again, yeah, if you give it one argument, it does the auto correlation estimate. Okay. Going once, going twice, 3 times. Okay, office hour tomorrow, 3 o'clock. Office hours are being recorded now, so you can review them later if you want to.
Thank you, Dr. Lush.
Yeah, see you guys.
Thank you.